So how does the electricity use during the day? These are what determined by the load curves. The top one is the average load curve, a typical load curve, for example, for the Southern California. We know that most of the electricity used around the noontime. When people are at work, all the factories are working, and basically the society is actively in the work and everything is working. In the early in the morning, about 3, 4 o'clock in the morning, people are asleep and the electrical demand will be reduced. So after about, in California, let's say in Los Angeles, the peak is about 1 to 2 p.m. Gradually after that, people, go home. The factories they shut down, and people they just need some energy for transportation and eventually for making cooking and so on. And then gradually it drives down until they reaches a minimum at around 2 to 3 a.m. The same thing, we have this is a daily load. We can also plot the annual load. And again, annual load depending on the seasons. In California, most of the load is in the summer because of the most of the air conditioner are running. In some place like Canada, the peak load in the winter because it's a cold country. So that is different from one country to another country. No matter which country we're talking about, these curves, they can show that there is a minimum amount of energy that has to be supplied at all time. This is called the base load. In addition to the base load, we have a period that the load is much higher, and we need, to be basically provided by other means. So those are the time of the peak loads. This is the annual load duration curve. Basically, it tells you the number of hours different power plant is running during the year. The run of river hydro, they run it all the time. You don't stop it. The nuclear pretty much is running all the time, 24/7. So is the fossil fuels, except maybe for a few days of shutdown. But then as we go to the other means of generating electricity, that is, for example, the gas turbine, diesels, fuel cells, these are the ones that are being used on demand. Whenever the peak load, we reach the peak load and the base load power plant cannot provide enough electricity, then we switch to the gas turbines, to fuels and other forms. Renewables are relatively, small, but expected to be increased and pay, and be more of our mix. Many places, all of these might not be enough to provide the electricity during the very, very high demand. In this case, some electricity has to be imported from the neighboring states. So this is indicated by imports. So depending on what form of electrical generation we talk about, if we have different capacities. Installed capacity is what the power plant was designed for, to produce the power at a maximum level. The peak capacity is a total capacity that a utility company can provide during the peak time, which could include the coal, oil power plant, and in addition to that, other forms of the power plant like the gas turbines and fuel cell, etc. A baseload capacity is a capacity that is pretty much being run throughout the year, mostly being provided by the nuclear and fossil fuels. And of course, the reserve capacity is what's remaining. It's stored on site and used, as is needed. Once electricity is produced, it has to be transmitted. Electricity, to reduce the losses, it has to be increased in the voltage to a very high voltage. The higher voltage means lower loss. So the electricity in the power plant is being jacked up to a very, very high voltage, several thousand kilovolts, and then sent through the high power transmission line until your destination. If the distance is very far, there are intermediate stations that you have to jack up the voltage to a higher voltage before you continue the trip. And then, so these would be the basically switchboards, intermediate stationary, then where the transformers increase the voltage to high voltage again to reduce the losses until we reach close to the your home. These are called the last mile delivery to the residential customers and maybe to industrial customers. And in there, you have to step down the transformer. You reduce the voltage to a safe level, 110 in the United States, 220 to the European, and sometimes 380 for industrial customers and very high heavy machinery, and being sent to the house. This is the what we call it is coming from the Ohm's law. We said that the total power loss is proportional to the resistance times the current square. The power you can resistance time current is called voltage, so power is a voltage time current. To have the same power being transmitted, the voltage has to be increased. So if the voltage has to be increased, the current has to be decreased. So we have the higher voltage I need or lower current. The power can be in the form of the direct current or alternative current. The alternative current means that the voltage is fluctuating between the maximum and minimum. In the DC current, the voltage is continuously at the same level. The AC has less transmission losses, so it would be more useful for long transmissions. DC is on the other hand is safer. I like you to read the book and look at the controversy which was between the Edison, which was using the DC power, and the Westinghouse, which uses the Tesla technology of the AC power. They were in the big competitions and sometimes was frighteningly hostile into providing the electric to the New York authority, and fortunately it was won by Westinghouse. But the controversy is very, very interesting, and I encourage you to read the book. Some of our devices work with the AC and other devices work with the DC. For example, our computer works with the DC. The lighting starts with the AC. So depending on whether we need the AC or DC, the AC has to be converted to DC and back and forth. This is usually done by the help of a rectifier. Electricity cannot be stored as it is. Basically, it is very, very difficult to store the electricity. We can store the electricity inside the batteries, but the storage capacity of the batteries are not very, very high. Pretty much the electricity that we're using right now to run this computer and to turn on our light as we speak, it was generated only a millisecond ago. And some places which could be thousands of miles from here. As electricity is generated, it has to be used. We can only, with a limited capacity, to store it through other devices. One of those is a battery, but it's not a very, very effective way. So there are other ways. We can store it in the capacitor. We can store it in the form of the magnetic energy storage device. We can store it in the flywheel. We can use it to compress the air. All of them can be done, but at a relatively low efficiency. There is a electrical analogy between electricity and basically hydraulic. In this example, we know that a pump is pumping the water from a low pressure to a high pressure, and then we store it in this container, in this tank, water storage tank. And then when we want it, the water can flow down and run a water wheel to produce power in this case, and then being returned, the power will be returned to the storage. The analogy would be a battery. The battery would be the analogous to a pump. As the pump increasing the pressure, the battery increasing the voltage. It's increasing the voltage from 0 volt, which is the ground, to 12 volt in this case. And so once we do that, we have to what? We can use it to basically run a load. Instead of the water wheel, in this case, we turn on the light bulb and we produce, we run the electric motor. So that would be our load. So as you can see that in this case, rather than having the flow of water, we have the flow of current. So current is analogous to the flow rate. Rather than increasing the elevation as it is in the pump, we increase the voltage elevation or voltage potential. Instead of the pump, we have a battery, and instead of water wheel, I have a motor. This table shows the power consumption for several household appliances. A clock is using very low amount of energy every second that it runs, or very low power. As we go through this, you can see that things like a radio, TV are relatively low power. Air conditioners, dishwashers, microwave ovens, dryers, they can go to very, very high power. So I would recommend that you walk around the house, you look at different appliances, and you find out how much power they use, and then find out how many hours a day you're using them, and from there calculate the total amount of the energy and the cost of running each of this equipment throughout the day for 1 day and for 1 year. That would be a very useful example. Thank you.